we will look at a few time scales of climate change. So for reference, we will look at this geologic chart going from Hadean, which I already mentioned as a hell, where continents were forming, volcanoes were going off, meteorites were crashing, and so on and so forth. The system originated around 4.6 billion years ago. Archaea is the beginning where early evidence of life occurs. So 3.8 billion years ago, gets moved a little bit, maybe life was found a little bit earlier than that. Middle Archaea, late Archaea, this whole thing is called Precambrian. As we mentioned before, we will see that again. Then came the Proterozoic, where the early evidence of life occurs, or this is the early life. So early Proterozoic, middle and late Proterozoic. And then came the Phanerozoic, or the visible life, where you begin to see evidences of fossils etched on rocks and so on. And Cambrian occurred right about there. This is called Precambrian because at the Cambrian there was a huge explosion of maybe 25 or more million new species. Okay, that's why it's called Cambrian, Post-Cambrian, and Precambrian. Then we have had Paleozoic, Mesozoic, and Cenozoic. You can blow up this last part, the Phanerozoic, and see the Precambrian here, where there is evidence of life, jellyfish-like radially symmetric things from the Ediacaran, which is a place in Australia 630 million years ago. Cambrian, evidence for first organisms with shells, trilobites, and then you go into Ordovician, Silurian, Devonian, and so on, where fish come along, first land plants, vascular plants, insects. So you have to think about evolution of life here, which is not directly related to us. But why would organisms develop shells? Basically because somebody was trying to eat them and they were probably trying to protect themselves with a shell. But such species still exist, and in fact those are the ones that leave geochemical evidence in the sediments, because those shells of calcium carbonate or silica have they are dependent on temperature, for example, and their abundance is dependent on the upwelling and so on. So you can look at their abundance and their crystal structure and say something about past climates. You can also look at delta O18, for example, to see whether there was extensive glaciation or not based on O18 depletions and so on. Insects, pollinators, so you have to always wonder whether the flowers came first or the pollinators came first. There is a story of oxygen evolution along the way. Dinosaurs dominated, they went extinct because of the meteorite crash around 65 million years ago. So that's the KT boundary, Tertiary Cretaceous boundary. It's called K because the C was taken up by somebody else before, I think the Jurassic Cretaceous or some other boundary. Okay, flowering plants, extinction of dinosaurs, explosion of mammals, and then humans came along at the very, very last stage, only about 0.01 million years ago. Some people show this as a 24-hour clock and say we arrived just at the last fraction of a second before midnight. Okay, within that the continents have moved. Okay, I will just go through few estimated locations of continents. 600 million years ago, you can see that there is glaciation in at the southern pole, but the continents are completely differently distributed, and they began to move northward. You can begin to identify various things by 280 million years ago. What can you see? Australia is somewhere here, Antarctica is still there, some deformed shapes of Africa and Europe there. I don't know, this may be you can guess what it is. There is Asia forming, Europe. This is the so-called Tethys Sea. There is the rifting of Africa on this side. North America is seen here. South America is seen. So when Alfred Wegener in the 1920s first looked at the continental configurations and said they have moved and before they fit together, people actually laughed at him. And it's only after he died that it was finally accepted that in fact continents float on top of the mantle and they indeed move. There is India making its move across the equator towards Asia. There is Australia moving north. So the connections between the oceans, the shelf areas, the oceans themselves were all different, which means the climates would have been different. At present, we are here. The connection between the Pacific and the Indian Ocean is blocked, for example. That would have affected the El Nino that we see at present would not have been there before when this connection was open. Mediterranean Sea now is locked up. Red Sea and Persian Gulf have formed, Gulf of Mexico and so on. Along the way there are many other changes. This link here between South America and Antarctica opened up and created Drake Passage, I think only about 60 million years ago. The Isthmus of Panama closed about 7 million years ago. These rifts also happened around 7 million years ago. This equatorial closing probably occurred about 5 million years ago or so, and so on. So these things are still moving north. So in the future, everybody will congregate in the north near the Arctic. So Australia, for example, moves northward at about 3 centimeter per year, I think. India is still moving north, so the Himalayas are rising by about 1 centimeter per year. India is subducting under the Asian plate and making lots of potential for earthquakes here, etc. And you can see the mid-ocean ridges where the ocean plates keep forming and they spread and they subduct under the continental plates and so on. So again, you need two things. You need to say, how do we know a continent was here, India was here before, and when was it here before? So if we say 65 million years ago India was here, we have to geolocate it and say its latitude is known, and we have to date it and say we know the time when it was there. So the timing is done with the isotopes we talked about, like lead and uranium and so on, which have long half-lives. I think I said lead before. It's uranium, which has a half-life of a billion years, and it produces lead, which is not radioactive. Okay. So the geolocating is usually done by looking at the magnetic fields in the rock. So you take out the rock from India, you date it. Let's say you find a rock that's 65 million years old. You look at its magnetic properties. If a rock is in the low latitudes, then its magnetic lines will have very low angles. But when it's at a higher latitude, its magnetic lines will have steeper angles. So this is one of the ways in which the location, latitudinal location, is identified and the dating is done. So just to quickly say, look at these different configurations of continents, and models can be run. In the models, numerical models, you can move the continents as you want and recreate the ocean configurations, and you give it the top of the atmospheric energy, and the model will produce the atmospheric circulation, ocean circulation, rainfall, ITCZ, and so on. And you can see that there were strong shelf areas, coastal upwelling areas, which are critical because they would have played a role in colonizing land. For example, an algae that was photosynthesizing in the ocean would have colonized land probably through the upwelling regions and with the sea level change and so on. So entire circulation would have been different, where it would have rained would have been different, and there is a combination of things that would determine the amount of CO2. For example, low latitude land would give more rocks in the warm regions with maybe more rain, so faster weathering rates and faster drawdown of carbon and cooling of the atmosphere, for example. Okay, all these kinds of details have to be understood when we go to past climate. So that's how a combination of geological and geochemical evidences are mixed with models to try to interpret past climates, estimate past carbons, and so on. There are just carbon models which do that. One of the carbon isotopes used there is called C13 to C12. Maybe we'll look at it in one of the later podcasts, but you can look it up yourself as well. Now you have all the basics you need to understand how isotopes work.